Dear students, in the last lecture, we had discussed a method to find out fz if u or v is given. The method was known as Mill-Thomson's method. Today we shall discuss another method for constructing the analytic functions. Suppose that fz is equal to u plus iv is analytic, and suppose that u is known to us. Now what is our aim? Our aim is to find out v, and if we know v, u is already given, so we can find out fz, which is given by u plus iv. Now dv is given by del v upon del x dx plus del v upon del y dy. Now by Cauchy-Riemann equations, del v upon del x can be written as minus del u upon del y, and del v upon del y can be written as del u upon del x. So therefore dv is equal to m dx plus n dy, where m is minus del u upon del y and n is equal to del u upon del x. Now if we differentiate m with respect to y, so we get minus del 2u upon del y square, and del n upon del x is equal to del 2u upon del x square. So therefore u satisfies Laplace equation del 2u upon del x square plus del 2y upon del y square is equal to 0. So therefore del m upon del y is equal to del n upon del x. So that means this equation number 1 is an exact differential. We have studied in BSc part 1. Hence we can find out v and thereby fz. So this is the method for finding out v, and thereby we find out fz. Let's take few examples. If u is equal to x minus 1 whole cube minus 3xy square plus 3y square, determine v so that u plus iv is a regular function of x plus iy. Now because u is x minus 1 whole cube minus 3xy square plus 3y square, so we differentiate it partially with respect to x, and we get it as 3 into x minus 1 whole square minus 3y square. And similarly del u upon del y is minus 6xy plus 6y. Now dv is given by del v upon del x dx plus del v upon del y dy, which in terms of partial derivatives of u with respect to x and y can be written as minus del u upon del y dx plus del u upon del x dy. Substitute the values. Minus del u upon del y is 6xy minus 6y into dx plus del u upon del x is 3 into x minus 1 whole square minus 3y square dy, which can be written as 6xy minus 6y dx plus, if you simplify it, this is 3x square minus 6x plus 3 minus 3y square dy. You can check that this is an exact differential, and say therefore we integrate this with respect to x, treating y as constant, so we get it as 3x square y minus 6xy. And in this expression we integrate those terms which do not contain x, so we get these two terms, 3 into y minus y cube plus c. So therefore if u is given to us, we can find out v. Okay, let's take next example. Show that the function u xy is equal to e to the power x cos y is harmonic. That means we have to show that u satisfies Laplace equation. Let's do the first part. U is e to the power x cos y, so del u upon del x is e to the power x cos y, and del u upon del y is minus e to the power x sin y. Differentiate it again partially with respect to x, we get del 2u upon del x square is e to the power x cos y, and del 2u upon del y square is equal to minus e to the power x cos y. So if we add these two expressions, we get del 2u upon del x square plus del 2u upon del y square is equal to 0. That means u is harmonic. Now in the second part, we have to determine its harmonic conjugate, that is v, and the analytic function fz given by u plus iv. So again we write dv as del v upon del x dx plus del v upon del y dy. Again use Cauchy-Riemann equations, get minus del u upon del y dx plus del u upon del x dy. Put the values of these partial derivatives, e to the power x sin y dx plus e to the power x cos y dy. Integrate it with respect to x, treating y as constant. So we have e to the power x sin y, and we will not get any additional term from here, so plus c. So therefore fz is equal to u plus I into v. U is e to the power x cos y plus I times v is e to the power x sin y plus c, which is e to the power x cos y plus I sin y plus I into c. I into c is again a constant. We write it as d, and cos y plus I sin y is e to the power I y, which can be written as e to the power x plus I y plus d, and x plus I y is z. So this is e to the power z plus d. So fz is e to the power z plus d. So this is the second method for constructing analytic functions. Now let's take some more examples which involve differentiability. Let's take this example. Show that the function f of xy is equal to xy plus iy is everywhere continuous but is not analytic. Now this is continuous because x into y is a polynomial. This is also polynomial. So comparing with fz is u plus iv, we have u is equal to xy and v is equal to y. So u and v are continuous because these are polynomials. So therefore fz is everywhere continuous. Now in the second part we have to show that it is not analytic. So we shall show that Cauchy-Riemann equations are not satisfied. So del u upon del x is y, right? Del u upon del y is x. Del v upon del x is 0. Del v upon del y is 1. So therefore del u upon del x is not equal to del v upon del y, and del u upon del y is not equal to minus del v upon del x. So therefore fz is not analytic. Let's take second example. Show that the function fz is equal to under root of mod xy is not analytic at the origin. Means we will show that function is not differentiable at the origin. Because if function is not differentiable, then it is not analytic, although the Cauchy-Riemann equations are satisfied at that point. So comparing with fz is equal to u plus iv, so we have u is equal to under root of mod xy and v is equal to 0. So at the origin, del u upon del x is given by limit x tending to 0, u of x comma 0 minus u of 0 comma 0 upon x. Now u at x comma 0 is 0, because if we put y as 0 here, we get u is equal to 0. U of 0 comma 0 is again 0 upon x. So therefore this limit is equal to 0. Similarly, del u upon del y is given by limit y tending to 0, u of 0 comma y minus u of 0 comma 0 upon y, which is again limit y tending to 0, 0 minus 0 upon y, which is equal to 0. Similarly, we will see that del v upon del x and del v upon del y, these are also equal to 0. So therefore Cauchy-Riemann equations are satisfied at the origin, because del u upon del x is equal to del v upon del y, and del u upon del y is equal to minus of del v upon del x. So the first part is over. Now in the second part we have to show that this is not analytic at the origin. So for that what we do is we take this limit z tending to 0, f of z minus f0 upon z minus 0. F of z is under root of mod xy, f of 0 is 0, and in place of z we substitute x plus iy. Now suppose that z tends to 0 along the line y is equal to mx along the radius vector. So then we have this limit as limit z tending to 0, fz minus f0 upon z minus 0 is equal to limit z tending to 0 Of course, you can replace z by x here because we are taking y is equal to mx. So this is under root of mod of m into, in place of y we put mx, so we have mod of mx square upon x times 1 plus in. So x gets cancelled and we are left with under root of m upon 1 plus in. Now this expression, this depends upon m, means it is not unique. So which is not unique, as it depends on m. So therefore this limit does not exist, means f dash at 0 does not exist. So that means function is not analytic at the origin, and thereby that means function is not differentiable at the origin, thereby function is not analytic at the origin. Let's take next example. If fz is equal to xy square upon x plus iy upon x square plus y to the power 4 when z is not equal to 0 and f0 is equal to 0. We have to prove that fz minus f0 upon z tends to 0 as z tends to 0 along any radius vector. Any radius vector means along y is equal to mx, but not as z tends to 0 in any manner. So suppose z tends to 0 along the radius vector y is equal to mx, then we consider this limit z tending to 0 fz minus f0 upon z. Now f0 is 0, and in place of fz we write this expression xy square into x plus iy upon x square plus y to the power 4 upon z, and z is x plus iy. So x plus iy gets cancelled. So this comes out to be limit x tends to 0 m square x upon 1 plus m to the power 4 into x square, and now when x tends to 0 this is equal to 0. But if we take any radius vector, no, in this case we have to show that along, but not as z tends to 0 in any manner. So suppose we take this curve y is equal to x, part of the parabola, then limit z tending to 0 fz minus f0 upon z is equal to limit z tending to 0 xy square upon x square plus y to the power 4. Now in place of y square we put x, so we have limit x tending to 0 x into x upon x square plus x square, which comes out to be 1 by 2. That means this limit is not equal to 0. So that's what we had to show. Okay, let's take one more example. If fz is equal to x cube y into y minus ix upon x to the power 6 plus y square when z is not equal to 0 and f of 0 is equal to 0. We have to show that fz minus f0 upon z tends to 0 as z tends to 0 along any radius vector but not as z tends to 0 in any manner. So let's simplify this. Fz minus f0 upon z, which is equal to fz upon z. Fz is this x cube y minus ix upon x to the power 6 plus y square, and z is x plus iy. Take minus I common from here. We have minus I into x cube y into x plus iy divided by x to the power 6 plus y square into x plus iy. X plus iy gets cancelled. So we are left with minus I into x cube y upon x to the power 6 plus y square. Now we have to show that this limit tends to 0 when z tends to 0 along any radius vector. So suppose z tends to 0 along the radius vector y is equal to mx. So in place of y, substitute mx. So therefore limit z tending to 0 fz minus f0 upon z minus 0 is equal to limit x tending to 0 minus ix cube into mx upon x to the power 6 plus m square x square. So we will get this limit as 0. Now suppose that z tends to 0 along the curve y is equal to x cube. So therefore limit z tending to 0 fz minus f0 upon z is limit x tending to 0. Put the values here. In place of y we put x cube. So we get minus x cube into x cube upon x to the power 6 plus x cube whole square. So which comes out to be minus I upon 2, which is not equal to 0. That's what we have to prove. Thank you so much.